So what we're going to look at is the assignment from week 9.1 Magnetism. There's a lot of three-dimensional right-hand rules that we use, and it's hard to try to visualize that without someone actually doing it for you. So what I have here is, with my camera set up, now we're all facing in the same direction. Up is up, right is right, down is down. What we do have are these two other directions into and out of the screen. So we always use the screen or a sheet of paper as our reference. So if I had a sheet of paper on the floor, on the table, up would be this direction, down would be this direction. So whatever workplace we are using, that is our reference. So to show an arrow up, down, left, right is very easy. To show an arrow in, what we commonly do is we show it with an X. That X kind of symbolizes the feathers or the fleshings of a bow and arrow. If you're to shoot an arrow, you're going to see the feathers. If an arrow were coming towards you, you would see the point. So dots are considered out of your workspace, and X's are considered into your workspace, because trying to draw a three-dimensional picture is not something that we can all do, and even so, you have to do it very well to actually have a good description and to have a good demonstration. So this is week 9.1. What I'm going to do is quickly go through worksheet 1. What this is looking at is the magnetic field around a wire. If we have all of the charges doing the same thing, whether they're all rotating the same way, giving us natural magnetism for iron or nickel or cobalt, or instead, if we were looking at a charge, a line of charges all traveling together, when they all do the same thing, we get magnetic fields. Now, the best way to do something like worksheet 1, the magnetic field around a wire, is to simply know that the shape of a magnetic field around a wire is simply going to be a circle. So if this pen represents my wire, I will have magnetic fields that are circular around that wire. The question is it circular in this direction, or is it circular in this direction? Because there has to be a direction for our magnetic field. So the reason what we use for the for the magnetic field around a wire is we use the first right-hand rule. Our thumb represents the direction of current flow. We have it listed as I. Direction of the current flow. I already know I'm going to see a circle that goes around it. The question is, which way does it point? Whichever way my right fingers curl. So I don't have to visualize a circle with my fingertips. The fingertips are just giving me the direction. I already know that it's going to be circular in shape. So in looking at some of these here, questions 5 through 8 are real good ones to start with. I have number 5, I have a current going in, so I know that I'm going to have a circle going around that wire. The question is, which way is it going to point, clockwise or counterclockwise? Well, current is in X. That's an arrow going away from me. So my thumb goes this way, my finger curl does something like that, which means that I see a clockwise shape. So I'm going to show little arrows that are tangent to the circle. So I'm going to have arrows going to the right and to the right, arrows going down and down. Down here, same thing as number 5. The only difference is I have twice the current. Twice the current means my arrow is going to be twice as big, twice the field. Here I've got a dot. My dot is a current coming towards me. My finger curl is showing counterclockwise, which makes sense. I would expect to see something opposite. So I'm going to show some arrows that are tangent to a circle that points up and to the left, up and to the left. Right here will be up and to the right, up and to the right. Now when you get to a question like number 8, now you don't have a wire going in or out. Now you're looking at the wire pointing up this way. And it's easiest to do this one at a time. So if I just simply look at one single piece of my current there. So I've got 2 wires, let's look at just one. These X's are just locations that are being marked. They're not X's showing anything that's going in like that one is. So if I look at a wire, I know to expect a circle. The question is, does my circle go in on the right and out on the left? Or does it do the opposite? Does it go in on the left, out on the right? So my current goes up, my thumb goes up, and my fingertips go in on the right-hand side, and I can see they're going to come out on the left. So I'm going to have in on the right side of each wire, and I'm going to have out on the left side of each wire. And you can look at my answer key to see how it is that we would show that with dots and X's rather than try to draw a three-dimensional picture. Moving down here, so again, up here, these questions, you have a magnet. Magnetic fields point where a north needle would point. Opposites attract, likes repel. So I would have arrows pointing away from the north, in towards the south, through the magnet. That's all in the previous note, so you can look at that. So question number 11 through number 15. So question number 11. Current carrying wire perpendicular to the page. Dot is coming towards me. I'm going to draw myself a circle that is counterclockwise. Number 12. My wire runs up and down. I know that my circular shape looks like this. So what I'm going to need to see is where do my field lines go into the page? Arrow down, thumb down, finger curl in on the left, X's, out on the right, dots. So in on the left, out on the right. So there are my X's on the left, dots on the right. I can apply that to two separate wires, and what we'll find is we'll get some locations where we have our field lines pointing together. If I have two different currents, I'll have some where they're pointing apart. And in the picture, in the notes for our magnetic fields around a wire, I show a progression of how you get from a straight line to a curved line. So now that we've seen the first right-hand rule in action, go back and now you can check out those pictures that we have in the narrated notes and on the PDF notes. What I want to look at now is the next right-hand rule, and that next right-hand rule is going to be, boom, right here. We call this one the third right-hand rule. So we have the first right-hand rule, which is finger curl, and we've got the third right-hand rule. The third right-hand rule actually applies to a mathematical concept known as the cross product. And if you know what a cross product is, in physics, we like using the stop hand. Thumb out to the side, fingers up, stop right there. That is the stop hand. Thumb is perpendicular to my fingers. My fingers are perpendicular to my palm, and my palm is perpendicular to my thumb. Three vectors that are all perpendicular to each other. Some teachers like using a finger coordinate instead. And so instead of a palm, we have our middle finger representing that third dimension. I'm not a fan of that one because it's really easy to kind of figure out which one, to mix up which one is which. So I go fingers, thumb, and palm. And a cross product is thumb cross fingers equals palm. That is a mathematical cross product. Thumb cross fingers equals palm. It's all about directions. So for us, thumb is going to be the direction of charge motion. All of our rules are based on positive charge motion, so whichever way my positives are going, that's my thumb. Fingers represent my magnetic field, so conveniently, fingers field. And the palm is going to represent the force experienced by the moving charge. Palm is the push, because a force is a push. Fingers field, palm push. Make sure you're using your right hand. What if I have a negative charge? A negative charge just experiences an opposite direction of force. So I still use my right hand rule. I get an answer, and I know, okay, a positive would be pushed this way, which means a negative would be pushed the other way. So I always use the stop hand of my right hand for my third right hand rule. Some people decide to use their left hand for a negative. I never ever do that. I am always right hand rule. So, looking at our worksheet here, I have my magnetic field, which is the letter B, which doesn't make any sense, but it is what it is. Let's see, magnetic field is out of the page and current is up the page. So I am not sure what has happened here when I open it. There's a lot of markings on here that shouldn't be here. That's strange. But regardless, so my magnetic field is out of the page. So my fingers, so we're all facing the same direction now. My fingers have to come out the page and my current is up the page. Notice I can rotate my hand any which way I want and keep my fingers pointing the right direction, the correct direction. So I want my fingers pointing towards me, current up the page. My hand looks something like this. My palm is going off to the right. Question 1, right. Question 2, B is into the page, fingers into the page with the X's. Current is up, thumb up, fingers in, and my palm goes to the left. 1 and 2 are opposites of each other. Hopefully that isn't a surprise. Change the direction of the field, keep everything else the same, and I should get opposite answers. B is out of the page. Current is to the right. Out of the page, fingers, thumb goes to the right. My palm is facing down the page. Down would be my answer. So 1, 2, and 3, I can see how I'm getting my answers. Continuing on down. Number 4, magnetic field is up the page. Current is going into the page. Now, if you have an actual sheet of paper, which I don't, and most likely you probably didn't print one off, that's okay. If I have a sheet of paper, I can rotate the paper around so my wrist isn't doing all these weird things. So B is up the page. Current is into the page. Doing something like that gives me a palm to the right. So my force is to the right. And I've said in my notes, magnetism is weird. It takes a field and a direction of motion that are perpendicular to each other to get a third direction for our force. It doesn't make any logical sense. Everything else up until now we could kind of put together and piece it together. Not this stuff. Question number 5. My number 5, let's see, B is down the page. So down the page. Current is to the right. So I got to kind of rotate my hand a little bit weird here, but I can see that my palm, when I do this, my palm, maybe like this is better. My palm is going into the page. So number 5, into the page. Number 6, current to the right, field to the left. They are parallel / anti-parallel. There are no perpendicular components. Cross product says answer is 0. Number 6, there is no force. So all I have to do is change the direction of one of my components, and just like that, I can get no force, which is weird. Number 7, B is into the page. Current is to the left. Well, that's convenient on my wrist. Palm is going down the page. Number 8, my field is to the right. My current is out of the page. There's a dot, and it tells me that it's out. So I rotate my hand this way. My palm is going up the page. Number 9, there's an extra step. I have to figure out the direction of the magnetic field near this magnet. A north would repel another north, which means my field lines point up and away. So up is my magnetic field. Current is into the page. My palm is going to the right. Okay. A south, my field lines point into a south, so that's going to be down, so my fingertips point down. My thumb has to point in, so in doing that, my palm goes to the left. Left and right, opposite answers. The only difference is north versus south, so that should make sense. So north, we said our field was up. Current goes to the right. My palm comes out of the page. Number 11 is out. Number 12, current is out of the page. Thumb, field, it's still in north, so my arrows point away from the north. My palm goes to the left. Notice 11 and 12 is just me going from number 11 out to 12 to the left. Moving down here, number 13 through number 18, what we're looking at now is we're looking at an individual charge, not a line of charge, but an individual charge now. One thing about the force on a charge is that because of the third right-hand rule, because everything is perpendicular, when you push on a charge, you are pushing perpendicular, you're actually going to cause a direction change, which means you only end up with circular motion for an individual particle pushed by a magnetic field. So it has to be pushed in the has to be moving in the correct direction to feel a force, and if it does feel a force, it is pushed into a circle. It doesn't get faster, it doesn't get slower, it just goes in a circle. So again, it doesn't make any sense, but that's just how magnetism works. 13, a proton moves to the right across the page. Thumb. Magnetic field that points up the page. Fingers. My palm is coming out of the page. So my proton will be pushed this way. Number 14, an electron moves to the right across the page. Field that points up. 14 and 13, they're the same. Palm comes out of the page. However, an electron is negative. So a positive would be pushed out of the page, which means a negative would be pushed opposite into the page. A wire has current that flows up the page. Back to a wire. Current flows up. An unknown magnetic field, so I don't know which way my fingers are pointing, produces a force that pushes the wire to the right. So instead of knowing my thumb and my fingers, I know my thumb and my palm. So third right-hand rule is just a 3-variable equation. You give me 2 variables, I'll tell you the third. So current flows up. It is pushed to the right across the page, so my thumb has to stay pointing up. It's hard for me to bend this way. We're going to try something like this. Thumb goes up the page, it's pushed to the right. Our field is coming towards us. Fingers field, so out of the page. Number 16 is interesting. A magnetic field of Earth points north. So when you are sitting in your classroom, you find north. That's the direction of our magnetic field because that's the direction that our compass points. So north. Which direction must you throw a proton so that it feels a force that points up? All right, so if we're in our classroom and this is to the north, that's our field. If I want something to be pushed up, my palm has to go up the classroom. So north, up, that direction there. If that's north, that's east. If I throw a proton to the east, it literally gets pushed up. If I throw a proton to the west, it literally gets pushed down. If I throw a proton north or south, no force. It's weird. Number 17, a wire has current that flows into the page through an unknown magnetic field. It is pushed to the left. So a wire has current that flows into, thumb goes in. It is pushed to the left, so something like this. So into the page, pushed to the left. My fingertips are going down the page. All right. So some examples there. Number 18, you can try and figure that one out. It's a 3-stepper. I got to figure out what direction my field points, and then I have to figure out which end, north or south, would give me that field. So I guess that's actually a 2-stepper, not a 3-stepper. So what we've just done is we have just done worksheet number 1, looking at first right-hand rule, and we looked at the third right-hand rule worksheet using, again, our third right-hand rule. So if you have any other questions, make sure you come to our Zoom meetings or send me a remind and we can have a discussion about that. So that's your first and your third right-hand rule. The third right-hand rule, the first right-hand rule is the magnetic field around a current carrying wire. The third right-hand rule is the force felt by an individual charge pushing it into a circle, or the force felt by a length of wire. If I have all these charges all moving together, they all get pushed in the same direction. So a wire doesn't spin in a circle, it just moves. An individual particle will travel in a circle. So you can only get good at this with practice. It's very strange. It doesn't make a lot of sense. So you got to practice and practice and practice. And that's what all these are here for your benefit to go through with solutions included. So that is week 9.1. So give it a try and good luck.